All right, so now we want to really talk about Einstein's famous equation, E equals mc squared. So here's a little background. So this is kind of funny, a virus. I didn't realize that was up there. Okay, so here's a virus. Of all the times to talk about a virus, right? So here's a virus about 10 to the minus 7 meters in diameter or something. Viruses are made out of molecules. Molecules are really small compared to that, right? So this is 100 times smaller than that. Molecules are made out of atoms. Here's an atom. Atoms are a tenth the size of a molecule. Okay, what's inside? What's in the center of an atom? A nucleus, right? But look, the nucleus is like a 10,000 times smaller than an atom. Who cares? But anyway, what's inside a nucleus? Protons, also neutrons. Now, when I was in high school, that's where it ended. So people knew about protons, neutrons, electrons, and things like that. But then actually, when I was in high school, people learned that there are smaller things inside protons and neutrons, and they're called quarks. Q-U-A-R-K, right? So quarks are 1,000 times smaller than a proton or a neutron. And right now, we don't know if there's anything inside a quark. So that's kind of what we're working on, with the particle physics experiments. But as far as we know, it's a quark, right? Now, there are six kinds of quarks. So they come in 3 generations. So the first generation, they were the first ones found, up and down. Second generation, charm and strange. Third generation, top and bottom. And there's 3 types of each quark, and they're called flavors or colors, whatever. All right? And they have different masses. These are the light ones. These are medium mass. These are the real heavy guys. So it's much more difficult to find the heavy guys than it is to find the light ones, And this was the last of the 6 quarks that was found. The top quark was the last one. It was discovered at Fermilab in 1995. And I want to tell you a little bit about how this experiment worked. Okay, so here's what they did at Fermilab. So Fermilab was built to be a proton accelerator. And so for many years, it was just, they just accelerated protons. And then they thought, well, golly, you get more bang for the buck if you have a head-on collision, right? And so they figured out how to produce antiprotons. And then they figured out how to have the protons go this way and the antiprotons go this way, and then smash them. So there's a lot of energy being generated when these things smash. Okay, so this is how they found the top quark. So you have an incredibly fast-moving proton smashing an incredibly fast-moving antiproton, and that right there, that's called an annihilation. So the mass basically goes away, and it's pure energy. And then that energy forms mass plus energy, okay? And so you have proton annihilating antiproton, and what's formed is a top and an anti-top quark. And these things, they decay, but we don't care. So the important thing is this. I have a proton smashing an antiproton, and you get a top and an anti-top plus energy. Well, we don't even care about the energy. All I care, I'm just going to write what's important, okay? Now, here's what's incredible. The mass of the top, by the way, so the mass of a proton and antiproton is the same. The mass of the top and the antitop is the same. It's anti because it has an opposite charge. So the antiproton has a negative charge. Okay, so here's what's incredible. The mass of the top quark is 182 times the mass of a proton. So that's why they drew the picture like this. So, I mean, I don't know if this is just an analogy. It might be totally wrong. So just imagine like shooting 2 marbles at each other and getting like bowling balls out. Now, what would your high school chemistry teacher tell you about that? Impossible, right? Because mass is conserved. Well, it's not conserved, So that's kind of cool, right? So here's the question. I mean, you know, all you're starting with is a little proton and a little antiproton. And then you're getting these gigantic top and antitop. Where did all that extra mass come from, right? This is a 1 proton, 1 antiproton. This is 182 protons. This is 182 protons. Where did all that mass come from? All that additional mass? Well, here we go, right? Here's our energy conservation equation. So this mass initial is much less than the mass final. So where did it come from? It came from this, right? So some of this initial kinetic energy was converted into matter. And that's okay, right? That's okay with relativity. So there you go, okay? So, and that's why it took so long to find that top quark, because they had to improve Fermilab so they could get those protons and antiprotons even going faster and faster and faster. So they had enough kinetic energy to be able to make the top and the antitop. So that's an example, right, of when energy was converted into mass, which is allowed by relativity. Okay, there's another particle. It's called a Z0. It was discovered in 1983 at CERN, Geneva, Switzerland. So it was discovered there, but they did most of the work on it at Stanford. So this is Stanford Linear Accelerator Complex, Stanford, California. So this is a 2-mile-long accelerator. This is 2 miles. There's a highway over it. Anyway, and so what they did, they use electrons and anti-electrons, which is called a positron. And so they smashed electrons and anti-electrons, or positrons, together to form the Z0. So this is how they did it. So just pretend the electrons are red, the anti-electrons are blue, right? And so they accelerate them on this 2-mile straight. Then the electrons go this way, and the positrons go this way, and they smash right there. This is many stories high. This is a giant building, you know, with this detector here. I don't remember how many stories, maybe 2 or 3 or 4, I don't know. I don't remember, but big. And they make the Z0. Okay, cool. Now look, the mass of the Z0 is 89,224 times the mass of the two, you know, of the electron and positron pair. 89,000. So that's like, you know, colliding 2 pieces of dust and getting a truck. Now I don't know if that's true, but it sounds good to me, you know. Wow, that's incredible. You know, 89,000. So again, where did all that additional mass come from? It's the same thing, you know. So this M initial is much, much less than M final. So where did the mass come from? So some of this initial kinetic energy was converted into the mass, which again is allowed by relativity. Okay, let's do something similar, but well, different. Now here, okay, they do this all over, well, whatever. So here's E plus E minus forming 2 gamma rays, right? So this has mass, this has mass. Gamma rays, that's light, photons, you know, no mass. So here you have something with mass, here you have something without mass. Where'd the mass go? Well, guess what, right? And so where'd the mass go? So here, this was equal to the mass of the E plus E minus. This is 0. So where'd that mass go? It went into the kinetic energy of the photons. Okay? So this is 0. And anyway, so that plus that went into the kinetic energy of the photons. By the way, if you've ever had a PET scan, this is the reaction that's used in the PET scan to create the image. So this is used in hospitals, you know. Okay, here's another example of mass becoming energy. This is our sun. So this is the sun when you're just looking at X-ray. I think it's X-ray wavelengths, I think. 4.35 billion kilograms of matter are converted into energy every single second. That's a lot. Well, luckily the sun is pretty big, So it's going to, you know, at this rate, it will still last billions of years. But that's what, think about it. Mass being converted into energy, or matter being converted into energy. And that's what it says, right? That's what it says, right? This can be 0 as long as this plus that equals that. All right, here's nuclear fusion in the sun. Why does the sun shine? Because of nuclear fusion, where visible light is produced. So you have 4 protons that repel, right? But if you're going fast enough and they're close enough, they're going to fuse together. And that's why it's called fusion. When they fuse together, 2 of the protons combine to make neutrons plus other stuff. So here it is. So you have 4 protons coming in, and then this is now this is a helium, right? And so you have a helium, and you have 2 positrons, you have some neutrinos, and you have visible light. Okay? Don't worry about the details. But here's all right. So here's what comes in. This is what comes out. Now here's the important thing. The total mass of all of this is 0.7% less than the total mass of that. So again, so wow. So some of the mass has been converted into energy, right? And that's totally allowed in relativity. Okay? So the important thing is that mass can be converted to energy. Energy can be converted into mass. Now here's a really cool quote. This is an awesome book, by the way, that anybody that's taking this class can easily, well, maybe not easily, but can understand. It's written for educated people, all right? It's called The Elegant Universe. There was a TV series on it a long time ago. But anyway, mass and energy are not distinct. They are the same basic stuff, packaged in forms that make them appear different. Just as solid ice can melt into liquid water, Einstein showed that mass is a frozen form of energy which can be converted into the more familiar energy of motion. So think about that. That's pretty awesome, huh? How are we doing in time?
12.
Okay, we're fine. We're good. Okay, so here's a problem solving. Let's just review this problem solving strategy. And, you know, and this works for most of the problems that you'll deal with. So you ask yourself, what are the 2 reference frames? What are the 2 events? Who or what measures the proper time or the proper length? Who or what measures dilated time or contracted length? Calculate gamma. Then just calculate whatever you need to. You know, delta t, delta tau, L, whatever. And if necessary, you might have to use that space-time interval. You might have to use Lorentz equations, you know, whatever, momentum, energy, whatever. You just got to do what you got to do. And this is a good check. Are the results consistent with Galilean relativity when the velocity is much, much less than c? That's always a good check. Okay, now just something that's kind of fun. Ooh, okay, so Einstein published relativity in 1905. So 1905, special relativity published. Now, at the time, there was no experimental verification of this at all. You know, it was just Einstein using logic, you know, and math. And so you can imagine that most people just didn't buy it. They didn't believe it at all. So, especially the Americans, because Einstein was a German Jew. Okay, that's another story. Okay, so 1911, there's an APS meeting in America, American Physical Society, big national meeting in the United States. And there was a guy from Princeton who was giving the presidential address. So that's kind of a big deal. And he was speaking about relativity. And he didn't believe it at all. So I just have a little quote, and I hope it makes sense to you. All right, so he's talking about relativity. So he's saying relativity really amounts to saying that experience is not a criterion of truth, and that we must rely on an inward sentiment of knowledge as revealed in subjective formulae. All right? So basically, he doesn't like relativity, and he's saying, look, relativity says you're going to believe these equations, and you have to disregard your own experience. So he doesn't like that. Okay, there's another one. All right. Undoubtedly, the German mind, Einstein, is prone to carry a theory to its logical conclusion, even if it leads into unfathomable depths, like relativity of time and space and all this stuff, right? On the other hand, Anglo-Saxons are apt to demand a practical result, even at the expense of logic. Can you imagine a physicist saying something like that? I mean, it's horrible. He's basically saying, you know, Einstein is wrong because he carried the theory through to its logical conclusion. And dumb Americans, which I am one, right, are apt to demand a practical result, even at the expense of logic. That's what he said. Kind of interesting. All right. Now, in 1921, Einstein received the Nobel Prize. Okay? And he felt strongly that he should have gotten a Nobel Prize for relativity. However, he did not. He got the Nobel Prize for something called the photoelectric effect, which we'll discuss in a few weeks or so. And he was rather unpleased about that. And so, when he received the Nobel, okay, so when you get the Nobel Prize, you give a speech. And typically you give the speech about, you know, why you obtained the Nobel Prize, you know, what you did to earn that Nobel Prize. So everybody that didn't know him figured that he was going to give the Nobel Prize a speech about the photoelectric effect, because that's what he got the prize for. But Einstein, being Einstein, feeling that he should have got it for relativity, when he gave his talk, he gave it on relativity, which is kind of funny. All right. Let's pause. Let's quit.